Okay, so this is a video that is discussing notes over carboxylic acids and their derivatives. In this is discussed the priority for nomenclature in organic chemistry, the reactivity of different derivatives of carboxylic acids, a little bit of oxidation, and a little bit of reduction. And there's some practice problems at the end. Okay, so to get this started, when naming organic compounds, there is a list of priority. Basically, if it's high enough in priority, you use its suffix name, and if it's lower in priority, you use it as a prefix. For example, if we have a compound that has both, let's say, a ketone and an aldehyde in it, so let's say something like, let's draw a 4-carbon molecule, where it has both an aldehyde and it has a ketone in it. Because aldehyde is higher in priority than a ketone, the aldehyde will dominate for the suffix. So we will end up seeing the al ending. So for example, this is 4 carbons. So this is butanal. And because we have a ketone, and ketone is lower in priority, we'll use the prefix name, oxo. So this will be on the 3rd carbon, because the 1st carbon will be where the functional group is at. So on the 3rd carbon, we have an oxo. So it'd be 3-oxo-butanal, and this is how you would name a molecule such as this. So the priority group is a way of understanding which just gets a suffix name and which one will get the prefix name. If it is higher in priority, it gets a suffix. If it's low in priority, it gets the prefix name. So the correct way of naming this is 3-oxo-butanal. In the context of this chapter, the most important ones to note is the carboxylic acid, the aldehydes, and the ketones, but you'll occasionally have alcohols get mixed in, you'll get alkenes, alkynes. Honestly, anything is fair game, but in this chapter, the biggest ones you'll see is carboxylic acids, aldehydes, and ketones. So you need to really understand how to go between the three. Okay, so moving on. Okay, so different derivatives of carboxylic acid. So a derivative just means that if I start with a carboxylic acid, I can get these other forms of it. So as you see this, like this acyl chloride can be reacted to form back into carboxylic acid, anhydrides can, esters can, amides can, they all can be converted back to this form, but this form can also be converted into each of these using different reagents. And it is worth noting how to do those as well. To form an acyl chloride from carboxylic acid, the reagent you need to use is a thionyl chloride, which is SOCl2, and that will form the acyl chloride. To form an anhydride, the typical steps for this is using dehydration mechanism or condensation reactions whenever you heat it up to remove water, which is why it's called an anhydride, because it's missing water. To form esters or even amides, use something that is analogous. In the case of esters, it is called Fischer esterification. In the case of amides, is a very, very similar mechanism in which this is actually reversible. Both of these are reversible. It can flip between the two products. The importance of the reactivity is that if you move it to a more reactive state, let's say like the acyl chloride, you can easily use this as a precursor for forming other molecules. Something you should be familiar with is oxidation and reduction. Oxidation can be defined as adding oxygens to a molecule or specifically to a carbon, while reduction can be considered doing the opposite. To add to that, reduction could also be considered adding hydrogen, while oxidation can be considered removing hydrogen. To show this in action, we have a primary alcohol. Under oxidation, we'll see an alcohol be converted to a carbonyl. So if we have a secondary alcohol, we get a ketone. If we have a primary alcohol, we get an aldehyde. But under most conditions, the aldehyde will further be oxidized to form a carboxylic acid. Most oxidizing agents will do this. Here, this just lists potassium permanganate and chromic acid, but there are other strong oxidizers that will do the same. Weak oxidizing agents, most commonly one used is PCC, will stop at the aldehyde step. So if you have a primary alcohol or an aldehyde and you mix it with potassium permanganate or chromic acid, it will fully oxidize to carboxylic acid. However, if you have a weak oxidizer such as PCC, it will stop at the aldehyde step. And again, for secondary alcohols, if you oxidize them, they form ketones. But if you have a tertiary alcohol, it cannot be oxidized. And that is because you have to have those hydrogens present as part of that oxidation step, which if we were to show a mechanism of that, you can see why they are important. So the opposite of oxidation is reduction. In reduction, we need to take these molecules with extra oxygens and remove them. We have various different types of reducing agents, and this is covered in notes that I got before this, so they're not present here. But what is worth noting is that a reducing agent such as sodium borohydride will reduce aldehydes and ketones, while lithium aluminum hydride will reduce everything. In this case, we have a carboxylic acid, so the presence of lithium aluminum hydride will fully reduce it down to an alcohol. Here we have another carboxylic acid, and again, lithium aluminum hydride will reduce it down to a primary alcohol. So in both these cases, they get reduced to alcohols. Sodium borohydride will not reduce a carboxylic acid. Okay, so now looking at some practice problems. So the first one says, draw an acetic acid dimer, be sure to indicate the hydrogen bonds present. Well, a dimer is just a molecule, well, two molecules that are linked together. Two identical molecules linked together. Let's be a little bit more specific here. So acetic acid has two carbons, has an oxygen, and then a hydrogen. And for drawing the dimer, we need to draw the opposite of this as well. So the hydrogen bonded to the oxygen, bond to a carbon, has a double bond to another oxygen, and then this. So we have acetic acid and acetic acid. What ends up happening is that hydrogen bonding occurs right here, and this is what forms the dimer. So this is not a true bond. This is a non-covalent bond called a hydrogen bond. But in reality, what can happen is that these can actually flip positions. So for example, the electrons here can grab onto the hydrogen and form a true bond, but when that happens, this has to break and come over here to reestablish double bond. This moves up, and if this is grabbing on here, these electrons move back down, and then these move here to establish a bond to the hydrogen. So what we can actually see is that these hydrogens can flip back and forth between which acetic acid is bound to. But none of that is necessarily important in your case. What you need to know is that hydrogen bonding does occur, which is why carboxylic acids have high boiling points. Okay, so where would you expect to find a proton NMR signal for the carboxyl groups hydrogen and propanoic acid? So we look at propanoic acid, we have 3 carbons, then we have our oxygen, our other oxygen, and then our hydrogen. So it is asking where do we expect to see this hydrogen? Well, this hydrogen has a few issues that come up with. One, it's next to a bunch of electron withdrawing stuff, so it's basically going to be horribly shifted. Second is that this can also move into solution, which can make it a little bit harder to find, because if this mixes in with, like, say, water, or say deuterium, because you probably do it with deuterium, you would see some interesting things occur. But in general, what you'll notice more often than anything, because the rest of it's just noise, and I actually have this here on the side, so... Okay, so when we look at propanoic acid, what we observe is that the peak happens about 12. And this is kind of be expected. It's definitely going to be anywhere past, you know, it's going to be shifted to the left, like horribly shifted to the left because all electron withdrawing material around it, and we kind of expected these to be in this area. So we knew it was definitely going to be somewhere past here because that's just in general what happens when you're next to highly electron withdrawing material. But in the case of acids, typically it is about 12. Moving on, we see 1 hexanols reacting with chromic acid to yield what product? Well, chromic acid is one of our strong oxidizers. And since this is a primary alcohol, what we'll observe is a formation of hexanoic acid. So 1, 2, 3, 4, 5, 6. So our current product looks like this, but after oxidation with a strong oxidizer, we observe the formation of a carboxylic acid. So this will be hexanoic acid. For this next reaction, we are taking a weak reducing agent, sodium borohydride, and we are mixing it with this molecule. Sodium borohydride can reduce aldehydes and ketones but cannot touch carboxylic acids. So what we end up observing is that this side is reduced while this side is not. So remember, the reduced form of a aldehyde or ketone is, or even a carboxylic acid for that matter, is an alcohol. So we will form an alcohol. So let's draw out the right side, which does not change. And then on the left side, so that's an acid. Left side, we have a secondary alcohol because a ketone is secondary, so its alcohol is secondary. For the next reaction, we're using lithium aluminum hydride. Well, lithium aluminum hydride is a strong reducing agent, so both sides get reduced. So we're going to draw out our benzene. Then on this side, we have a primary alcohol. My mouse is acting up, my bad. Okay, so here we have a primary alcohol. And on the other side, we have a secondary alcohol. Of course, I can draw on the hydrogens if I wanted to, and there's a CH3 over here. But yes, so carboxylic acid becomes a primary alcohol. Pretend like that's an O. My mouse acted up, so CH2OH. And on the other side, we just see a secondary alcohol. So we have a COH here where the carbonyl used to be. Okay, and the next one is a naming exercise, or I guess drawing from a name. We have pent-3-enonic acid. Well, we can see which has the highest priority, the oic acid, which we already know because carboxylic acids are at the top. And the Y means we have a triple bond. Okay, so let's see. So pent-3-enonic acid. So let's start by drawing our primary functional group here. Okay, so this is carbon 1. We have carbon 2. But on carbon 3, we see a triple bond. So we go to carbon 3, 1, 2, 3, and here we see a triple bond. So 1, 2, 3, 4, and then one more makes 5. So this has 1, 2, 3, 4, 5 carbons. So we have all the carbons present. We see the carboxylic acid is present. That's on carbon 1. And we see on carbon 3, we have the alkyne. So this is our molecule that we're looking for.